I can't find it if I don't do it first. Not up there. Okay. Which group would have the highest priority? Okay, do you remember what CHO means? Yeah. That's kind of essential to know that. I'm getting 19. Does that feel right? Okay, do I got 3 more? All right. All right, it's either A or B. I would consider that good way to, you know. All right, so we've got C double bond O H. Okay, and here we've got C H H. So when you go one step away, we've got C's. We actually have 3 C's, right? Okay, then what do? We're going to take the double bond O, and what are we going to do? Swap and fill. So that means that on this C, we're going to put in, and on the O, we're going to put a C. All right, so the next options are going to be O, O, yeah, and H. Okay, over here, we had a C. Okay, that's this one. Now, what are our options? Okay, BR, H, and H. Okay, so you're looking for the point of difference. There's 2 points of difference, right? So which one do you use? The biggest gun. Okay, so what's your biggest gun here? An O, and here it's a BR. Which one has the highest atomic number? BR.
So it doesn't matter that the other one had 2 O's.
No, the fact that there were 2 is irrelevant.
Okay.
You can only bring 1 gun to the battle. You don't get 2. You only get 1.
Well, I put BR. Just make it.
Okay, and it might come up in the homework. I can't remember if it did or not. But what if you had this and you had this? What is D? What is D?
D.
Anybody know?
Item and D. Both parallel.
No. In other words, if you had that's going back. It's just kind of sad. If you have that compound, is there a chiral center in it? There is. Which one is higher priority, H or D? What is D?
I don't know.
Have you heard of that? Deuterium? You've never heard of deuterium?
It's not even up there. Yeah.
It's a hydrogen.
No, what is it?
Isotope.
It's an isotope of hydrogen. Okay, what is T? Tritium. There's hydrogen, deuterium, and tritium are the 3 isotopes of hydrogen. You should have talked about them in Durkheim when you talked about isotopes. Okay.
I'm a fail.
You know our answer.
Okay. So that's all right. That's what I'm telling you. All right. How many protons does hydrogen have? It has one, right? How many protons does deuterium have?
One.
It has one, but it also has one neutron. This one doesn't have any. Okay. Tritium has 2 neutrons. Okay, so just so you've
Oh,
heard of
that
it.
means proton. I thought you were giving him points.
P plus, you did proton, neutron, electron. Well, blame the smartboard. Okay, so if you have these two, they're not identical. So deuterium will have a higher priority than hydrogen. Little hydrogen always loses. Okay, so just in case that comes up in chiral center stuff, I can't remember if it did or not, but it may come up in.
What are the formulas?
What do you mean? It just has a D. So like this would be CH4ClD. When they do formulas for organic compounds, they always put the carbons first. Oh, I'm sorry, it was C2, my bad. I was all worried about counting the hydrogen. They put the carbons first, and then they put the hydrogens, and then they put the rest in alphabetical order. So if you have to look something up in a book, okay, that's how you arrange it in order to find it. Okay, there are books that will list things in order of their molecular formulas, and so they always have CH, and then the rest are in alphabetical order. It's just like a standard, but somewhere they adopted. I don't know. I just do what they tell me. Okay, what is the absolute configuration for the chiral center? What? You like it? I know, I am. I'm falling over. Oh my God. And there's no D in it, so.
I know, I'm like using my pencil. Yeah, no, I'm like closing my
My iPad keeps going like this. See the molecule in three.
Well, you guys. Back here just like
All right, got one more. Someone just one thing. At least pick B. I mean, and if you nothing like a 50-50, is there?
47-50. So.
Well, our number isn't divisible by 2. So. Okay, so let's do the priorities first. Okay, so you should know the priorities from the last question. Anybody? Okay.
Yeah.
All right, so who's 1? The one with the BR is 1. All right. Who's 2?
Joe.
Good old Joe. Who's 3? And what's that poor little hydrogen? 4.
Yeah, because I was like picking it up.
Okay. So I have to put this in the same orientation as that. So I've got my red going back, my purple and my green in the plane, and my white one going out. All right, so I'm going to grab which one? White. And I'm going to hold it away from me. You see what happened? Okay, what happened to this one? It went up. Okay.
Okay, I was spinning it. I don't even know how that happened.
Don't be spinning it. All right, so here's one. Oh, that's 3, and purple
Well,
was
majority
2.
put S.
So what did we get? Is that clockwise or counterclockwise? Clockwise.
All right, that doesn't make any sense.
Why? What part doesn't make sense?
I don't see how you're holding it like that. Like even when you hold it like that, like to me, like if I was doing it, I would not hold it like that. I don't know.
You have to hold it like a bouquet. That's
Yeah, I
the
get
rule.
that, but like
Okay, 1, 2, 3.
I just don't. I don't see how you.
Can you start it how it was originally was and then show us?
All right, so here is the way it was.
Okay.
Okay, plain right here. Going back, coming out. I'm going to pull this one away.
You're looking at the
1, 2, 3.
I can't hold that. I swear.
You're
Hold it like this.
See if you go like this.
See, I don't know why, but like every time I want to do it, I
It
want to like.
goes the opposite direction.
I just want like this, like.
It doesn't matter how you move it. It does matters that you hold number 4 away from you.
As long as you point,
Remember, it's all connected. So when you move 4 away,
the red is going to go to the purple, which is going to go to the green. No matter which way you spin it and turn it, look at that. As long as the white is away from you.
yeah. You have to look straight at it with 4 away from you like a bouquet. Okay.
Okay.
What is that?
What?
And that.
Enantiomeric?
Oh,
We could find that last time.
No.
It's kind of a term.
It's a non-superimposable mirror. It has a non-superimposable mirror. Is that one R or S? That one R or S?
Some people
Lordy, and what's the right answer?
Yeah.
What's that?
Mm-hmm. I gotta know what they mean.
I just eat it. Oh, yeah.
I'm
Pretty bad. Not even tell me, it's a big old jumbo.
Okay, we're up to 14.
I'm not now. This one's easier because it's not, you don't like.
Why is it easier?
Because you just move to the middle.
That's what we did in the other one.
I think this one a whole lot easier.
We're gonna move the whole thing in this one too.
Here, you can have this back.
You have to pull the hydrogen back. You have to do that on this one too.
I just don't.
Hey.
Yeah,
Oh,
I just don't know why,
but that's, they've done that already.
Right.
I got 18.
I mean, actually,
Okay.
Oh, that's
well,
better.
that's
Well, if it's right, yeah. We're gonna figure it out. Where'd my little pen go? Okay. Okay, so which one up there is 1? Okay, who's 2? This one's 2. Who's 3? And then that poor little hydrogen is 4. Okay, so what does the picture mean?
The H and the B are coming out.
Right, we're going out. And what are the methylene bromide and the methyl doing? They're going back. Okay, so I'm going to hold this so that it's the same way. Okay, and which one am I going to grab? What did you get? One, 2, 3. So what is that? Okay. You got to know what that picture means, and you've got to orient number 4 away from you. That's the biggest thing for these. Okay. So one thing about enantiomers, they're non-superimposable mirror images. They have the same physical properties. So in other words, they have the same boiling points. They have the same melting points. They have the same densities. There's only one thing that's different, and that is that they rotate plane polarized light in opposite directions. Oh, of course. Now, who thought to put it in there and look? I don't know who did that first. I should try to find out. It kind of like blows the mind. Okay, now, do you remember what plane polarized light is? Okay, that's in the next slide. I have little pictures. Are you writing?
Yeah.
Like a lot?
A little bit.
Okay. I'm surprised you were writing so much. Okay. A substance is considered optically active if it rotates plane polarized light. So if I have this enantiomer, okay, this would be an optically active molecule because it will rotate plane polarized light. Okay, so when you have a light source, you get light coming out of it in all directions. You put some sort of polarizing filter, and that only allows the light traveling in a certain plane to go through. That's plane polarized light. Okay, make sense that much? Okay, so what happens is to rotate it, you're going to put a tube in there. And in that tube, you put your sample containing your chiral compound. And depending on how many of those compounds it sees, it's going to turn one way or the other. Okay? And this is you looking at it. There's like a, I've actually done this. There's like a 360 degree, and you can see the line from the light, and you can see how it shifts. Okay? I did a lab one time, and I still remember, it's like the only Echem lab I remember, but we took sucrose and we put an enzyme in there. That's probably why I remember it, because that's the cool part. And when you put the enzyme in there, it converts it from one enantiomer to the other. Okay, and it's timed, and you can watch on the polarimeter, it's doing the reaction in the tube, and you can watch it go to the other side. So you know when it's done because it's gone all the way across to the other side, the same number of degrees. Enantiomers rotate the plane polarized light the same number of degrees, but in opposite directions. So if one is plus 20 degrees, the other one is going to be minus 20 degrees. And what means plus and minus? Plus means dextrorotatory. It rotates the plane polarized light clockwise. Minus is levorotatory. It rotates the plane polarized light counterclockwise. Generally speaking, these will be designated with italicized letters, or sometimes I've seen the L, this is really light, cursive, and the D kind of cursive, okay? Okay. If it does not rotate plane polarized light, it's called optically inactive. If it doesn't rotate plane polarized light, does that mean it isn't chiral? What do you think?
it doesn't.
Rotate plain polarized light. Does that mean there's like no chiral centers in there?
No, it just means
What if I had this and I had the mirror image and I had both of them together in my mixture? One is rotating it this way, the other one is rotating it this way. So what happens to my rotation? I get 0, okay? That is referred to as a racemic mixture or racemate, okay? To designate when you, if I was to go buy this molecule, okay, it's going to be a whole lot cheaper for me to buy it as the racemic mixture, the racemate. I will have both of them in there together. But what if I want to make a drug that has a specific chiral center a specific way? I have to buy only the one, okay? The racemate is going to be designated D, L, or that plus minus. Usually they don't use both. Which one you use is kind of irrelevant. It doesn't matter. But if you want to only buy one of them, you need only the D or only the L. Okay? Which one rotates the plane polarized light clockwise and which one rotates it counterclockwise can only be determined by doing it. Okay? So if I have two enantiomers and I know that they're going to rotate at 20 degrees. I don't know which one is going to be positive and which one's going to be negative. Which one is dextrorotatory, which one is levorotatory. The only way I know that is to go do it or to look it up in the book because somebody else did it, okay? But there isn't a way to look at the structure and go, oh yeah, that one's going to be dextrorotatory. But if you know one, now you know the other one is the opposite. Is that making sense? People want to say, if it's R, it's always dextrorotatory, and that's not correct. It changes depending on structure. There's too many variables, okay? If you know the R one is dextrorotatory, then you know the S one is levorotatory or minus, okay? So a racemic mixture or racemate is a 50-50 mixture of enantiomers. Because we are chiral beings and we have all these chiral centers in us, your enzymes and proteins and the way that you work involves usually only one enantiomer. And your body will only use one enantiomer, okay? Here is how we actually test them in a polarimeter. A polarimeter is what we use to measure optical activity. The length of this tube can vary. Okay, the length of that tube can vary. Okay, typically the light source on all of these is a sodium line. I think it's the D line. Okay, but how many molecules the light beam encounters will determine how much it's going to rotate. So if I make my solution a certain concentration and you make your solution twice that, the amount it's going to rotate is going to change. And so because of that, they came up with a standard. This is the standard, okay? The alpha in the square brackets is your observed rotation. Is the specific rotation. So let me write that up there since so this is the specific rotation. So what we wanted to do was be able to put them all on the same scale so that we can compare our numbers and stuff like that. Okay, this is the observed rotation. C is your concentration in grams per milliliter of solution. Okay, that's kind of a weird one. It's not molarity, it's gram per milliliter in solution, okay? And L is the length of the tube in decimeters. Also, kind of weird. Okay, but I think most of them are 1 decimeter, and that's why they went with it, because they could divide everything by 1. But you can have different lengths of tubes. which will change what your observed rotation is. But when you put all those in there, you're going to be able to calculate your specific rotation. Okay, so here is S minus 2-butanol and R plus 2-butanol. Okay, this is the specific rotations for them. And what that means is that stands for specific rotation. The 27 is the temperature, which is pretty much room temperature. Okay, and then that D is the D line of sodium. Okay, so did you ever talk about atomic spectra? Did you ever see any atomic spectra where we have the tubes in there of the gases of the different elements, and you put a little electricity on, they light up, and then you get a specific spectrum off of that, and we split it out into the colors, and you get those lines. Okay, sodium has like 5 lines, I think, and the D line of sodium is what was used as the light source. Okay, that's all that D is. That's what that big D is. Okay, notice that the S1 is minus 13.5, so the R1 is plus 13.5. You took a sample of 2-butanol, you put it in a polarimeter, and you got 0. What does that tell you? You have 50% of it is the S, and 50% of it is the R. Okay, what if you did it and you got 10 degrees, plus 10 degrees? What do you think that would tell you? That you've got more of the R than the S. Okay, that's called enantiomeric excess. In the laboratory, we strive sometimes to make only one enantiomer. Okay, but your bodies can do it perfectly and only get one enantiomer every single time. Okay, so in the lab, they're busy developing methods in order to get only one enantiomer and not the other one, because separating them is really difficult. If you have a racemic mixture and you only want one of those to use, then you have to separate them. And the only thing that's different about them is their chirality. So what you have, there are different ways to do that. One is to use a column that you did TLC, right? Didn't you do the TLC lab already? Okay. Did he talk about column chromatography too? That's where you take the powder and you put it in a column. You can buy columns that the powder has chiral things on it, okay, like attached to it. And so they would then interact with those two things differently, and so you could separate them. And what happens is you run a solvent through it and you collect stuff in little vials, like a buttload of little vials. And then you test each little vial to figure out where your stuff is, run them all together. Okay, so, but that's difficult to do and expensive. Okay, those chiral columns are real expensive. Okay, in order for a compound to exhibit optical activity, it has to have at least one chiral center, and it has to have one enantiomer present in excess over the other. In excess over the other. Enantiomeric excess tells how much of an excess of one enantiomer is in the mixture. So it's the observed rotation divided by the specific rotation of the pure enantiomer times 100. So if you got 10 degrees, okay, on that last one, 10 divided by 13.5, sorry, I'm not good at that. 74%. Okay. So that means you have 74% of one enantiomer in excess over the other. Okay. So if 74% isn't, what is the remainder? What is the remainder 26%? Is it the other enantiomer?
Yes.
No. It's the racemic mixture. This is what's in excess over this one. Okay? Because they're canceling out. 26% is canceling each other out. Okay? So how much, if it was plus 10 degrees, okay, how much do you have total of that one enantiomer in your vial test tube bottle? You have 74 plus 13. So you have 87% of R. I don't remember what the plus one was. Was it R or S? You'll have it right there. It's R. Okay. So you would have 87% R and 13% S. See how we got that? Because this tells you how much is in excess. What's left is the mixture. So everybody strives to get a really high number, obviously, like 99. Everybody wants 100, okay? Sometimes in order to do some of these things, what manufacturers are doing is they are using bacteria to make that step, okay, to do part of the synthesis. They genetically worked on the bacteria so that they will make what they want in the chirality that they want so that they can get 100%. Okay? Now, why do we worry about, oh, we're going to do a problem? Let's do this first. When one of the enantiomers of 2-butanol is placed in a polarimeter, the observed rotation is 4.05 degrees counterclockwise. The solution was made by diluting 6 grams of 2-butanol to a total volume of 40 mils, and the solution was placed into a 200 millimeter polarimeter tube for the measurement. Determine the specific rotation for this enantiomer of 2-butanol. Okay, so how do you do it? Okay, since it is levorotatory, it has to be the -1. How do you know it's levorotatory? The counterclockwise part. The counterclockwise part. Okay. Okay, we're going to dilute 6 grams in 40 mils. Remember that the concentration has to be grams per mil of solution. Okay. So it's 0.15 grams per mil. That's your concentration. Okay. The path length, the length of the tube is 200 millimeters. Okay. So that's telling us that it's 2 decimeters. You know how big a millimeter is? Right? You know how big a centimeter is? Okay, do you know how big a decimeter is? This is big. Okay, that's a decimeter. So if it's 200 millimeters, it's that big, which is 2 decimeters. Okay? Yes. Or 100 millimeters. Okay, so what did you get for your number now? If you calculate the specific rotation, what was the little equation? Alpha equals, alpha in the square brackets equals alpha divided by CL. Okay. So is that sample the pure enantiomer? Yes, it is, because you got the minus 13.5. And that's how you would check. It's one way that's real simple to check. You also don't lose your sample, okay? If it took you 3 months to get to that sample, the last thing you want to do is have some way of figuring out that it was the right thing and then using it all up. So on these, you dissolve them, and then how do you get it back out of a solvent? You rotavap it, okay, and you get your stuff back. So you can still have your special stuff that you worked 3 months or years to make, okay? Don't spill it. Just saying.
Where did we get all of
Somebody put them in a polarimeter and got the numbers. That's where the numbers are from. They're from doing it in a polarimeter.
So like the path link is from a polarimeter?
Right.
Oh, okay, so we didn't have to
No. No, and this is how they dissolved it. Sometimes you dissolve it based on how much you have. So if all you have is 1 gram, you probably dissolve the whole thing, okay? And sometimes you dissolve it by how soluble it is in the solvent that you're using, okay? Any other questions on that? Okay, 30% enantiomeric excess. You have 70% racemic mixture and 30% excess of 1 enantiomer. The specific rotation of S2-iodobutane is plus 15.90 degrees. So is that dextrorotatory or levorotatory? Dextrorotatory. Determine the percent composition of a mixture of R and S 2-iodobutane if the specific rotation of the mixture is minus 3.18 degrees. We did math today. But they like to put proms like this on those tests. Okay, what does the negative sign tell you? Which one is an excess? So which one is an excess? R or S? Which one is an excess, R or S? R, because the S one is positive, so that tells you the R one must be negative. Okay, one goes this way, one goes the other way. Okay, so we know that. Okay, so now that we know that, how can we figure out what the enantiomeric excess is? So what are we going to do? Yeah. So, but what numbers do we divide? We divide the 3.18 by 15.9. Okay. Times 100, and we get 20%. What is that?
That negative sign. We don't bother that negative sign.
No, I wouldn't worry about it. The negative sign, all it's for is to tell you which one is an excess. Okay. So this is telling us that we have 20%, what? Enantiomeric excess, okay? So which one is 20% more than the other? The R or the S? The R, okay? So what is the other 80%? Yes, the other 80% is a racemate. It's shorter. The racemic mixture. So how much R is in our whole thing? 60% R and 40% S. See how we got it? The racemate is 50-50. So what's half of 80? 40 plus 20 is 60.
So why do you have up here at the top 65?
Yeah, it was.
That was another example. This was the problem. That was just another example. That was, what does 30% an enantiomeric excess mean? It means 65% of one enantiomer and 35% of the other. Okay, because 30% is one and 70% is the racemate. Okay, racemate is 50-50. So you have 60% R and 40% S. Kind of running out of room over there.
So what does the positive 15.9 tell you that it's?
That is this, the specific rotation of S2-iodobutane.
Yeah, but doesn't that tell you whether it's lead or
Yeah, the plus tells you it's which one, levorotatory or dextrorotatory? Okay. You did an experiment with 2-iodobutane. You're trying to figure out how, if you made one isomer over the other. If you made them both the same, 50-50, what would our rotation have been? It would have been 0, okay? But we got negative 3.18. So that means that we made one enantiomer in excess over the other, okay? This is how you figure out what that percent is. You take that number divided by the actual specific rotation that you probably looked up in a book, okay? So you take that number divided by that number times 100, and that gives you the 20%. Okay? How do you know that the R is in excess? Because it's negative 3.18, not positive. If it had been positive, the S1 would have been in excess.
But you only know that because you know that the 15.9
Yes, yes.
is S.
Yeah.
So if you weren't given that, you couldn't know.
You couldn't do the problem. Did that make you feel better?
Yeah, because like, they're not related. You said like.
No, I can't tell you of RS and you would have a 50-50 guess as to whether it was the plus or the minus. Okay, the only way to know is to do it or look it up. Okay, that's really the only way. Yeah. Yeah, you have to be given like data. Okay, we're not gonna like throw you to the wolves yet. Yeah.
Next semester.
Yeah. Okay, so why do we worry about this? Here's one of the reasons we worry about this. This is a compound called ibuprofen. Have you heard of it? Okay. When you did the TLC lab, I was going to say Tylenol lab. It's not really that. Ibuprofen, was that one of your standards? Yeah. All right. Did anybody find it under DL plus minus? There is a chiral center in that, right? Looky there. Oh my gosh. I don't know. Okay, everybody see that's the chiral center. Okay. Ibuprofen, only the S isomer gives pain relief. Only the S1 does. Okay. But when you buy it, it's sold as a racemate. It's sold as the 50-50 mixture. It's easier to make and makes it cheaper. Okay, if you could only give people the S isomer, it would be real expensive. Okay, so
Is that why fast acting is more expensive?
I don't know. I don't know what fast acting means. Okay, much of the R enantiomer, when you take that racemate, is converted to the S enantiomer in your liver. Okay, and so you get a little more than half. So if you're taking 500 milligrams, okay, 250 are R and 250 are S. Okay, only the S one's giving you the pain relief, but a lot of the R is going to get converted to S in your body, so you're going to get a little more than 250. Okay, I don't know what that percentage is. I've never seen that. Okay, anybody hear of this drug? Thalidomide, ever? Not heard of it? Okay, it was a big deal in my generation. Okay. Did everybody find the chiral center? Does everybody see that that's the chiral center? Did everybody see that's the only chiral center? Okay. Okay. This drug was given as a racemic mixture. Okay. It was cheap. It was given because it is a sedative and anti-nausea drug. And what do a lot of pregnant women have in their first trimester? A whole lot of nausea, okay? The R enantiomer is a sedative. It was used in Europe and Great Britain in 59 to 62. The S enantiomer is responsible for 10,000 cases of serious birth defects. Okay? And we are talking birth defects like someone was born with no arms. Someone was born with no legs. Someone was born without either arms or legs. I mean, it's like really bad birth defects. Okay? When something causes birth defects, it's called a teratogen. So we say this is highly teratogenic, this compound. Have you heard that term before? May not have yet. Okay. We now know that the R enantiomer also is a mild teratogen, and both enantiomers interconvert in the body. So even if we had isolated only the R and given people only the R, oh my gosh, we would still have had birth defects. The birth defects were so specific that they could go to exactly when you took the drug, and you, like if I took it 4 weeks in and you took it 4 weeks in, and then we looked, the babies would have the same birth defects. Like it was that specific. Pretty amazing, okay? This drug is cheap, okay? I mean, it doesn't look like it would be cheap, but it is cheap. It has been approved to treat leprosy and melanoma with strict regulations, okay? And it is being given overseas. And there have been some more signs of birth defects showing up. So there's a big push to totally, globally not allow anyone to use that drug. This is why we're doing this topic, because something can be bad, something can kill you, and the other one can save your life. Okay, and that's a problem. You'll see that a lot of medicines are one enantiomer or the other. And if they are only one, it's expensive. The cost jumps. All right, Monday. See you Monday. Okay. Oh, that's nice.
I'm not gonna block him. I'm not that bad, but I'm definitely gonna ghost him. It's Halloween, so festive.
See if he shows back up for this again.